morning, everybody. I'd also like to start by acknowledging the traditional custodians on the land on which we meet today and pay my respects to their leaders, both current, past and emerging. My name is Melissa Ryan. I'm the Director of Incubation and Entrepreneurship here at Macquarie, and we run 2 incubators here at Macquarie University, and the investment that we put into startups and innovation here is significant. We have a traditional incubator, but we also have a deep tech incubator, and Monomic and Glytherix is actually a member of that incubator. I am very excited to be chairing this panel today. I am not an expert in semiconductors. I know you're probably shocked to hear that, but the more I'm learning about it, the more I am excited by the opportunity it represents, and the opportunity also that what it represents specifically for Australia. I think that one of the greatest untold innovation and commercialisation stories of Australia is the discovery and commercialisation of Wi-Fi. Not only do I talk about it non-stop since I found out that Australia did it and that Macquarie played a significant part in that, I'm surprised that a lot of Australians don't know about it. And when I travel internationally representing Macquarie, I haven't met anyone internationally that knows this story. So I wanted to make sure that we got an opportunity to tell this story today, and we had a chat, Devor and I, and thought, well, why not? And we also have an event coming up in November around semiconductors. So I would like to introduce David Skellern. I don't think many people in this room don't know David. He's going to tell us about the history of the commercialisation of Wi-Fi and Macquarie. And I'm also happy to be joined by Jason Thelander, who's the Chief Technology Officer of Memjet. I'd like to kick off with you, David, because I'd really like to hear the story or the history and a brief overview of Australia's Wi-Fi discovery and commercialisation journey and your role as a Macquarie academic in that development and commercialisation.
Is this on? Yep. Great. All right. I've got to rattle through this because it's a long story. But it started a long time ago. I worked for a lot of my early life in radio astronomy. I did a PhD in radio astronomy, but I was much more interested in building the telescope, and that's ultimately constructing things, building things, designing things was what I was good at. I worked with a lot of other really wonderful Australian radio astronomers, all of whom seem to be able to do astronomy and build telescopes as well. And we all learned a lot about advanced signal processing, radio receivers and the like. I was at Sydney University. I went overseas. I intended getting a job overseas, and I did a sabbatical leave at Hewlett Packard Labs in their Networks and Communications lab, and they offered me a fantastic job. But I forgot to bring my wife along with me, and she didn't want to live overseas. So I came back to Australia to finish my time at Sydney University and look for something else. Bob Frater, who was from CSIRO and had been my PhD supervisor, decided to start investing in universities, not the group of 8, basically, because he couldn't get any traction with them. And he chose a few smaller universities, Macquarie being one of them, and he funded a chair in electronics, and he badgered me to apply for it, which I eventually did. And so in mid-89, I took up the chair of electronics at Macquarie and started building a new department. And CSIRO, through Bob, had told me that they would increase their support for my research, which they had been supporting at Sydney Uni. But they wanted me to do something that was not esoteric, like Model 1 transistors and building circuits that nobody really understood. And so I had, when I was working at HP, seen a visionary video, one of these, a lot of them were around in 1987, 88, on the future of the IT sector. And HP's was called 1995, Apple did one called Knowledge Navigator, and other companies did them. Anyway, I happened to notice at one point, about the 6th or 7th time I'd seen this 15-minute video, that there was just an assumption that these computers that they were plumping around on people's desks weren't plugged in. So they had a power cord and that was it. And it just occurred to me that that was a bloody good thing to think about how you do. So that was a seed that was stuck in my brain in '98. And when I came to Macquarie and looking for a thing to do, I thought, well, wireless networks would be great. Now, you've got to remember at the time, 1989 was the first real portable phone, right? A small thing, about as big as your hand, like an iPhone now, right? And it's different shape, but that was the first really portable device, real portable mobile phone. And so to think that what you might be able to do is, and we set out to design a circuit, something that could actually run as fast as the wired networks of the time, which was 100 megabits a second. The only radio systems that were out there that could transmit data that you could buy off the shelf were going at about 100 kilobits a second. So we were a long way from that. But CSIRO funded my work. They said, oh, well, okay, let's get going on that. But you've got to convince this guy over at the division, the radio physics division, that you need to work with him, collaborate, right? And so I went and saw this guy called John O'Sullivan, who I'd known when I was doing my PhD. He was in the same place I was at Sydney Uni. And he said, and I said, look, I was thinking we could work on wireless networks. And he said, funny you should mention that because we started work on them 6 months ago. So that was the beginning of a beautiful friendship. And so they funded my team at Macquarie. We put in the first CRC proposals that came up, Ralph Slatcher, the chief scientist, developed this CRC program, Cooperative Research Centres program. I talked CSIRO, they don't look at it this way, they now claim they did it, but I talked CSIRO into joining me in a bid for a CRC, and I brought a few companies with me that I'd been interacting with, and they got some companies together, and we put in a bid, and we got culled in the first cull. It was called it was going to be called the Centre for Local Environment Communication Technologies, right? Wireless, basically. Nothing was called Wi-Fi then, of course. This is 1990. So we got culled, and then, unbeknownst to me, 9 months later, John had revved this bid to put in a whole lot of other aspects other than the wireless, a lot of the applications that you'd use and, application-based work in networking. And I've forgotten the name of the head of CSIRO, but he had just joined CSIRO, the new CEO or whatever they called them of CSIRO at the time. He did a 3% levy on all of the industry, all of the divisions, and they had to come up with mega projects that would change the world to get any of their money back. And so John had revved our CRC bid quite substantially, but the core of it was the thing that we then did was wireless LANs, and CSIRO funded the program. It was called PLANS, the program for LANs and I can't remember what, but networking. So they had a criteria, and so then we worked. Our Macquarie's side of it was we had the team that I put together. Basically, I put together a bunch of academics and people we were working on who addressed all the different aspects you needed to do wireless LANs. The RF side, the digital side, blah, 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 networking side. What we worked on, but fundamentally was, from Sydney University, I brought a very large simulation package that allowed us to kind of build systems and model them in the computer, design and build and model systems. So that was our contribution to the program. That we knew a lot about radio links because we'd been working in satellite communications. And we were able to design in the computer, with very joint collaboration with CSIRO, a complete system to do wireless LANs. CSIRO built a lot of equipment to do the tests on it and get all the modelling of the propagation you needed. And then 3 years in, CSIRO had to have a partner, an industry partner, a major industry partner, to be able to continue the program. They didn't get one, and the program was stopped. But the then head of the Division of Radiophysics came to me and he said, these people are crazy, we've got to keep doing this work. And the next step is we need to actually take your models and build the real systems, right? And we said, yeah, good. He said, well, CSIRO didn't tell me I had to stop funding Macquarie University. So he doubled the money he gave me. And we had 8 people working full-time, plus PhD students, plus the academics that Macquarie had hired. And we'd taken it about as far as we could in the university until when in 1997, something very important happened. Al Gore and Bill Clinton had promised that they would put, when they were elected, they'd put the internet into every school in the US. And when they started to do that, they discovered that pretty well every school in the US had asbestos in the walls. And so the notion of wiring them all up with Ethernet was just not on, right? So we still didn't have any Wi-Fi, and in 1997, that wasn't around still. What happened is that the US allocated 200 megahertz of spectrum, like valued at the time compared to, you know, your mobile phones, it was valued at about $200 billion, right? Well, they allocated this spectrum in record time, took a few months. Through the Federal Communications Commission, a totally independent body, of course, not open to political influence. And so we thought, my God, here's the opportunity we needed, right, to be able to actually do this commercially. So myself and another professor that I brought in from overseas, a guy called Neil Westy, and the guy that at the time was heading the CSIRO effort, we formed a company called Moderator and started working on the chips. Well, we'd already started building the chips, excuse me, in Macquarie through the research money from CSIRO. We then really raised about $1.6 million to fund the company to begin with, because we sold just the modem part. We sold 10 modems for $100,000 each. And we were very valuable at the time. And then we managed to attract some multiplier funds from a thing called the START grant, which became the GERD grant, which then became this sort of neutered commercial ready thing that finally has been gotten rid of. So that gave us $1.6 million. And we had 6 employees and started, you know, driving through, demonstrated a small system. We went through a number of stages, but let me just say that by a year later, a year and 15 months later, we had a demonstration that could actually show in something about the size of a milk crate and have a transmitter at one end and a receiver at the other. It was still pretty big, but we could show that this was actually possible, right? Because a lot of people didn't think you could do it. And then we raised $8 million US from 2 US investors, companies. They were both trade investments. One was Cisco Systems, the other was a company called Broadcom, now owned by Qualcomm. And a year later, we got our chips back. So, and they worked first time, which is absolutely remarkable. But it was because of all the modelling and simulation work we'd done. And at that point, we needed to scale. Unlike most startups, the market was 10 times what we put in our pitches to investors, and it was growing even faster. And so just to meet the requirements, the product requirements for the orders that we had, was going to cost, you know, like $50 million. And we needed to raise a heck of a lot of money. We couldn't raise it in Australia. We started looking overseas. We tried in Australia. We found people who wanted to do it, but then Cisco just came and said, you know what, we just want to buy you. And then about half a dozen other people said, we want to buy you too. And so there was a bidding war, and we finally sold for $560 million. So we had intended trying to take the company public and to build a chip company in Australia, but that didn't happen. And all my efforts since then to do the same sort of thing have also ended up the same way. Well, the good ones. There's been the failures, total failures. All right, I'm going to stop there.
Thank you. I think it's very enlightening for everyone to understand what Australia can actually do if it gets the right support and unlock the vast amounts of money that we have saved up for super. I think could make a big difference. I think we're fast forward to today. And I'd like to ask Jason the role of semiconductors that play in MEMJET's printing technology, such as your new generation MEMS and CMOS wafers. I hope I'm pronouncing it correctly.
You have. So printing is not a terribly attractive industry. I mean, you all have printers at home, but there's an awful lot of investment and technology that goes into creating those things. That $59 printer you buy from Officeworks has probably taken about $2 billion worth of investment to get there. Most of that gets taken up in the development of the silicon wafer. So all printers, Hewlett-Packard, Canon, others that have thermal-based inkjet technology, they all use silicon wafers for their printing devices. They all sit on plastic substrates or metal on in-house. And you package those wafers onto a substrate and pass ink through, then it goes onto the page. It is an incredibly complicated process. It's not just file print. There's a lot of magic happens between the mouse click and the paper coming out. We tend to operate in commercial printing, which is large and fast. We print up to about 300 metres a minute print speeds, which is not your home printer. But the role that silicon plays for us is that silicon is the major cost. It's the highest BOM cost item on your printer, no matter who you are. And getting that wafer scale. So the bigger the wafer, the cheaper the chips ultimately, but the technology that's used to create the CMOS and the MEMS structures required to nucleate the bubble to throw the droplet out is very complicated and it's very expensive to set up. We don't have an option in Australia for our technology. Much like every other story, we've required investment. We've had to go overseas. It is an Australian technology, MEMJET, but it had to be funded by the US because the scale of investment was simply not available for the risk profile in Australia. We're the result of about $2 billion worth of investment into Australia. So having a local capability would be highly sought after. I personally don't think that printing will ever be a focus for Australia, but certainly we've heard a lot of medical stories and medical and health sort of stories for Australia. That is where I think we have a lot of technology play and a lot of skills in areas where you look at microfluidics, sort of shrinking down the analytical components and control factors for making some of the pharmaceuticals that we have in this area. That's kind of where I think the wafer sort of scale needs to go for Australia. But for us, we just take our 8-inch wafer that's worth a few $1,000s and we take the chips off and package them onto our printhead and then just wire them up. It does allow us to have a lot of technology to look after the print itself so they can run very fast. We put technology in the printing chip itself, not just a MEMS heater. It's got CMOS, which means logic, so it can run like a small computer, for lack of a better description. So we feed data and power in, and then we can generate drops when we need to as the printer goes past very fast. Not very attractive, but highly technical.
Yeah, well, I mean, I suppose that sort of comes to the next question. It's basically semiconductors are critical to our day-to-day life and are critical for the next chapter of innovation generally across almost every field. I want to know a little bit more about the development of these technologies, of what's actually happening in the space. I think it was really interesting having a chat with you, David, that you basically said the only thing that semiconductors aren't in is toothpaste. So I wanted to understand a little bit more about what are the trends and what's actually happening in the space and what those trends could potentially mean for Australia.
Well, Semiconductors have been remarkable because of the continual improvement in the capability of the semiconductors. And one of the measures of that is the number of transistors you can get for a given amount of money. There's a thing called Moore's Law, which many of you might have heard about, which was fundamentally an economic law, an observation by Gordon Moore that every 18 months you double the number of transistors you get for the same dollar you had previously. So that continued through until about 2008. So we had 50 years, or 40-something years of, 50 years of that growth. So that's extraordinary, right? Just mind-boggling. And I found it mind-boggling, especially since throughout my whole career everyone said, well, now we've reached the limits. And you don't tell a good PhD student there's a limit, and they go and work out how to go beyond it. And that's just happened so many times in my life. So when that stopped happening, people started to look at growing, building bigger and more capable chips. In about 2008, they started doing it by not doing a single die, as they call them, a small chip, but placing multiple chips inside what looked like the same package you had before. But in fact, what they'd done was connect them all up very closely, and increasingly they did 3D integration of them. So they put one chip on top of the other, so that the wire lengths weren't centimetres, they were microns. And so what that does is reduce the power you're using by a factor of 100, roughly, or up to 100, but certainly, you save 95% of the power if you do that. And it also means you go much faster. So you could start to get the performance and to build the density of stuff you were building with these multi-chip packages. Silicon, think of it this way, systems in package. So previously people were always looking at systems on chip, and then from about 2008, these very bespoke designs that were extremely difficult to do and very expensive were starting to emerge. We didn't even know it at the time. The companies kept it quiet. That's continued to be the case, so that now everything, all the top-end things, all the AI stuff, they're starting to put hundreds of chips in a single package. And it still looks like just a big version of those chips you might have seen, right? But they've got lots and lots of stuff in them. And what's happened is the manufacturers and the CAD tool providers have developed the capability to support that type of design and manufacturing. It's much more complicated than doing a single chip. But now, just to take an example, you can take a batch of chips and have them look like a single chip in a little cube and put them together with a technology called hybrid wafer bonding. To do that in 2010 cost you hundreds of millions of dollars. Nowadays you can buy a machine for $3 million that could do 20,000 chips like this, make them 20,000 a month. And that advanced packaging technology is essentially taking what used to be what was called the back end of line of a silicon wafer processing system and putting it together and just using that and expanding that. The big advantage of that also is that you don't have to just use silicon. You can use other technologies, and so you can integrate multiple different technologies, different compound semiconductors, photonics, MEMS, all sorts of stuff can be put into these silicon in package systems. And the great news for us is that that's exactly what Rob Stokes and his people funded in the Advanced Manufacturing Research Facility out at Bradfield, which is now, they've turned the soil on the second building of that, and that's being built. And so we expect that to come online about 2026, 27. And that gives us the capability of actually doing prototyping and small volume runs. And then hopefully that'll mean we'll get a lot more people designing clever systems in chip. And that means that we should be able to get industry and the government interested in sponsoring much larger facilities, because it's just a scale up of what we're going to have at the AMRF. At the moment, if you wanted to build a facility to do that, it's a fraction of the cost of actually doing the transistor end of it, right? So the modern state-of-the-art transistor fabrication system, you know, a plant will cost you $50 billion. You might get out of it for 40. But that's what it costs to be state-of-the-art. Now, we have good partners, US, Taiwan at the moment, you know, other places that do this. There's very few people know how to do it. And TSMC, Taiwan Semiconductor Manufacturing, is the world leader in it. So if you can get their core chips, they can be super AI type chips, NVIDIA type chips, if you can buy those as die, and it will be the case that we can do that. Maybe not the most advanced, but very advanced chips. Most stuff, when you build it, you don't need to use very advanced chips. Most of it's, you know, bread and butter stuff. It's really very simple. It's not simple, of course, but compared to those state-of-the-art things, it's very difficult. They're very simple to do. And the packaging is where the world's going to. So the very first conference, industry conference, to recognise that this advanced packaging stuff was going to go viral was in January 2022 in the US. It attracted something like 10,000 people to it, right? And the prediction now is that within 10 years, half the world's chips will be produced as silicon systems in package. So if we play the game right, Australia's very good at designing systems, electronic systems. We put them all in packages instead of on circuit boards. We can start to actually play a game and have a role in the global semiconductor supply chain. And I really believe that that's a serious possibility. We just have to focus on it and execute.
Okay, there's a question now for you, Jason. So has the integration of advanced robotics and AI in your North Ryde factory impacted your semiconductor manufacturing processes?
Yeah, so automated manufacturing certainly has. So we obviously take silicon wafers in. We are effectively a packaging house. We don't create the wafers. We design the chips. And TSMC make our base level seamless wafers, and they go to a Malaysian company called Silterra. They put MEMS on top, and then they go back to Taiwan, then they come to us. The reason why we're using robotics for our assembly is because we need to be cost competitive. Australia's not a very competitive manufacturing site if you've got a global sort of supply chain, or you want to interact with other countries for your technology. So we use robotics to reduce headcount for manufacture, because we need to be at least 1 to 5 reduced headcount to have competitive cost products for manufacturing overseas, because we sell into China, into Asia and US and Europe. And we need to heavily leverage automated assembly systems to get our overall manufacturing headcount down. I completely agree with David that we are very good at designing chips. There is an awful lot of technology that comes out from either microfluidics, health sector, advanced electronics, that does go into that packaging space, not necessarily in the manufacturing, but certainly in the design. Australia is a very well respected design house for the rest of the world, which is actually why it's much easier to get funding from overseas, because Australia does have a very high profile in terms of intellect and being able to get high technology platforms off the ground and successfully implemented.
That's super exciting.
It is.
Yeah. And watch this space. We have a really exciting announcement from Macquarie University in this space, which will be happening in the next couple of weeks. Any questions from the floor? Oh, we have one.
Thanks a lot. So how worried should we be about the threat posed by China to Taiwan?
The elephant in the room.
So it is a very real threat. I mean, if you were Taiwanese, you probably would have been a bit nervous a few years ago when Xi Jinping was to say, I don't really need to interrupt Taiwan economically, I can just bomb the top part of it, and then the world semiconductor industry is in disarray. TSMC provides about 60% of the world's high-end semiconductors. for the leading edge type process nodes, the smaller ones. MEMJet, we are looking at other options as moving CMOS into other areas aside from Taiwan. So certainly Malaysia, there are a few foundries in Europe. There are 10 in Australia, unfortunately, but we are certainly considering other options. It is something that is potentially an issue. Do I think it will be an issue? No. I don't believe it will be. I think there'll be too many other challenges for the rest of the world to worry about where semiconductor packaging is going.
Yeah, and I'd note that TSMC, with very large investments from governments, are building plants in 3 other parts of the world. So Arizona, Dresden, and one I'm not supposed to know about.
Let's hope you don't get shot on the way out.
Well, and also that is only the major technologies, though. They're not. Most of the chips that we use today and used are older process nodes. Like ours is a 0.35 micron process node, which is pretty old technology. The newer foundries that are being set up that David mentioned, they're all the 90, 45, 5 nanometer, very low process node technologies, which are very expensive.
So leaning into quantum.
Well, smaller process nodes.
Okay.
Yeah.
See? No, nothing.
No. Yes.
Hello?
Well, enabling
Yes.
that technology. Yeah.
One more question, sorry.
Hello, thank you. Will Schmidt from Investment New South Wales. Thank you very much. Question for anybody, Mel, yourself included, maybe. I think you also have a strong opinion on this. For me, hearing and David, thank you for the recounting of the full story, because I think the circuitous paths that we see successful platform technology development take reminds us about both the hard and soft innovation infrastructure that you need to make these things happen. So my question is, in semiconductors, from whatever angle, what do you think the next stage, if you had a magic wand, of hard and soft infrastructure development needs to be in order to enable actual platform industry flourishing in Australia?
Personally, I think the MEMS area is probably the one we should focus on. It is the lowest investment cost. Typically, we are 1 or 2 zeros short in terms of investment to get the other end of the process involved in or set up in Australia. And I think that's probably the most advanced space. If you're looking at everything's around sensing, everything's IoT, and we want sensors and process control and things for home medical or having diagnostic devices that are cheap and disposable. That's all enabled through MEMS technology.
Yeah, look, on the hard side, I think the getting behind this New South Wales effort in the Advanced Manufacturing Facility, but building the workforce that's going to be needed is hugely important. Over the past decade, we've seen a reduction from something like 24 universities teaching electronics to 5. There are only 5 universities in Australia now take electronics through to a final year of engineering degree. That is unbelievable, but it's true. And I did a tour of many of the universities when I took up the role as chair of the Semiconductor Sector Service Bureau. And so I went and looked at those universities, right? And they're fantastic, the ones that are doing it. And the other ones, honestly, it's just, I mean, they teach electronics at junior level, but I was, what's the word, gobsmacked, right? I really just didn't believe that this was true, but it was. What are they doing? AI.
Yeah.
You know where they're going to go without big semiconductor chips? Nowhere.
Nowhere. Yeah, I think the other elephant in the room is the investment in innovation. And I think what's happening in the tertiary sector now with our universities, they're becoming smaller. And when we mean smaller, that means they're offering less subjects. So less opportunity for our children to get educated. And it also means a lot more expensive for our children to get educated. And we cannot afford for only the richest, smartest minds in our country, because we're small. We need all of the smartest minds in Australia to be leaning into, commercialisation and inventing of technology. And I think that we have a huge opportunity, but we need to be backing our universities in no uncertain way, because there won't be the talent. Even if we do invent something, it will mean less likelihood of invention, and then we certainly won't be able to commercialise it here. So therefore, we don't get the jobs. That's my opinion. Thank you. And I don't have many opinions, as you can probably pick up. Thank you very much. And thank you very much for these wonderful individuals that have shared some amazing insights into an area that many people have no idea about, including myself. Thank you.
Thank you.